Okay, so good morning, everyone. Welcome. On behalf of the EnerQuality team here, we are very excited to be delivering another one of our Ask the Expert series sessions. This one is Building Better, Unlocking Energy Efficient Homes with Smart Insulation Solutions, and it is featuring our friends at DuPont. My name is Joanne Ferraraccio. I am the Education and Events Manager with EnerQuality, and we are very happy to have everyone joining us today. So a little bit about us here at EnerQuality and what we do. Many of you joining us in the room are familiar with EnerQuality, but I also noticed on the registration report a lot of new names, so it's exciting to see everyone. So a little bit about what we do. We, of course, deliver program administration. We deliver third-party programs that demonstrate value. Of course, we partner with OHBA, NRCan, Enbridge, ISO, and TAF. We also, of course, are very well known for the building certification and labeling that we do at EnerQuality as a qualified net zero service organization. Over 90% of the homes that are labeled Energy Star have been certified with EnerQuality, and we are very, very proud of that. And we also are very well known for our education and custom training, such as the webinar that you're seeing today. We deliver we work with builders, architects, energy advisors, and we are very proud to be working with many partners across the board, including Building Knowledge Canada and our manufacturers and suppliers such as DuPont as well, to bring to you education opportunities that are going to help you with building better and learning about different things that you can do within the industry. So in terms of our labeling and certification, you can see those here on screen, the different types that builders have access to through EnerQuality, as we do also our quality assurance for those labels. And we also, of course, are going to dive into a little bit of housekeeping. So when it comes to labeling and certification too that we deliver at EnerQuality, if you have any questions about that or the custom training, you can always reach out to our team. Mainly, you can reach out to training@enerquality.ca, and I'll make sure that I respond to that, or I will be able to connect you with one of our team members who will be able to appropriately support you. So let's dive into today. So a little bit of housekeeping. As I mentioned, as people started to come into the room, we're going to have some time for Q&A, and we do encourage you in the Zoom toolbar, there's a Q&A section, so please try to use that. You can ask, the bonus about it is that you can ask your questions anonymously if you wish. So ask your questions. We're going to hold those questions likely until the end. And Guy will be able to dive into those questions with our panel and kind of address those at that time. We'll make sure that there's also some time for it. So ask your questions following this session as well. For those who are joining us, you're also going to have the opportunity to receive a link to the presentation. So you don't need to take pictures or screen grabs or anything along those lines. Scribble down some notes if you wish for your questions. But by all means, you're going to receive a link to the presentation afterwards. And you're also going to receive contact details for Guy and for Eric so that you can reach out to them directly and ask your questions as well. And there will be a survey link. Because we also appreciate the team at DuPont and the team at EnerQuality. We appreciate your feedback whenever we deliver these workshops. So I'm going to launch a poll because before we get into introductions as to who's joining us on our panel, you can see everybody. But before we do that, I know our panel is very curious to know who is in the room, the virtual one, and who we're talking to. So please take a moment. It isn't a test. You might wear more than one hat, so please do respond to this poll quickly. We're going to leave it open for about 30 seconds or so, and I'm eager to see how many different roles and titles we have kind of in the room today, Guy. So let's give it another couple of seconds. We have about 75% of people who are in the room responding to this survey, so that is awesome. I say survey, I mean poll. So let's get a few more responses in there, and I will close this out in 3, 2, and 1. Thank you so much. And I'm going to share this with the entire room here. So Guy, Eric, Gord, you should be able to see, and the whole room, you should be able to see who's joining us. So the majority of those joining us are architects and designers. We also have a strong majority from builders as well. and some EAs in the room too. So this is great. If there's any others, you can definitely drop that in the chat just to let us know. We might not have covered it. So I'm going to stop sharing my screen there. But Guy and Eric, that gives you a little bit of a baseline as to who's joining us this morning.
Yep.
We'll get into some introductions. I'm going to hold Carrie. I'm going to just introduce everybody really quickly. I'm going to hand over to Guy so that Guy can start, and we'll kind of go from there with our introductions. So we have Guy, who is Senior Research Engineer with DuPont Building Solutions. Also joining as special guest this morning, you have two on your panel, Guy. You have Eric Lavoie from DuPont Building Solutions, and also Gord Cook. Many of you in the room know Gord. President of Building Knowledge Canada, and also close working relationship with EnerQuality, as well as one of our instructors for our courses. So Guy, I'll hand back over to you for some introductions.
Yep. Thank you, Joanne. I'm Guy Titley. I'm an engineer, and I've been actually with Dow Chemical since 1974 in various roles in the construction and either application or product development and basically technical service in all major markets, residential to commercial to geotechnical. I've ever since was DuPont. I still basically kept the same roles. I'm bilingual, so I'm able to answer questions in both languages, as is Eric. So that's all I want to say here.
Perfect. Okay, over to Eric.
Mute.
Yeah,
You're on mute.
sorry about it. Eric Lavoie, professional engineer as well, graduate and kind of the civil engineer. Work all my career almost on a technical sales kind of role, could be more commercial sometime, more technical to other times. Starting with Dell as well at 2009, so I got about 18 years experience now with DuPont as well as a building envelope for both commercial application and also residential application. So right now my role is to work with Guy and others to cover all kind of technical needs that we may have at DuPont across Canada, and some extended duty as well for commercial roof in the United States. Thank you.
Okay, perfect. Thank you, Eric. And over to Gord Cook, President of Building Knowledge Canada. Gord, a little intro from you.
Morning, Joanne. Nice to see you. Thanks for hosting. Gord Cook, Building Knowledge Canada. We're an energy advising firm, registered energy advising firm, work with builders across the country, frankly. I do a fair bit of work in the US as well. We like helping builders build better houses. I love the building industry. What could be more noble than building houses for generations of families? We just like to help builders with, we always say to them, let's keep you out of trouble and let's find new opportunities to build better houses. And in this context, insulation is one of those things that we chat about because insulation doesn't break. You put it in your house and it stays there for 300 years. So let's get it right the first time. So thanks for including me on this webinar.
Perfect. Thank you. Okay, so everyone too, before I hand over to Guy to dive into everything, I'm going to we asked one other poll question, and it kind of helps us set the tone. It's going to help Guy also with understanding kind of where things stand too. So we'd like to ask the question to all of you, where do you see the biggest challenge when it comes to insulation and building envelope performance? I've framed this question so that you can select more than one. But please take a few moments, everyone, to respond to this one. The options that we have here: managing thermal bridging, achieving consistent air tightness, moisture management and durability, meeting evolving code requirements, balancing performance with cost, or coordination between design and trades. We've kind of tried to hit on most of those buckets. If there's any outlier, though, drop that in the chat or put it in the Q&A. And we'll be able to make sure that we address that as well. But I see about 50% of everyone who's in the room has responded to this poll so far, so that's great. Would love to get 100% participation, I really do. Just because it isn't a test, we really do appreciate your feedback with this, and it kind of helps set the tone. So I'll leave this open for another couple of seconds as everyone is reading it through. We have about 3/4 of everyone responding. And I will close this out. hopefully everybody can see it on your screen. If you're not able to see the poll come up on your screen, if you want to drop your answer into the chat, that's also an option too. So I'll leave that open for everybody too to do that. So I'm going to close this out now in 3, 2, and 1. All right. And Guy, everyone on the floor, hopefully you can see this on your screen, the results. Can you see that?
Yes.
Okay, perfect. So it's a good mix here. What are your thoughts, Guy?
Well, that's good. I think, I have every one of those items, perhaps maybe not so much the cost issue will be addressed in what we're talking about today.
Okay,
I do
awesome.
like to point out, just let the record show that 10, 11 in the morning, builders and architects asked about the cost.
Right?
Yeah.
I always got to talk about the cost, which is fine. I get it.
Always got to cover it, Gord.
I get it. Yes.
You know what? It would have been funny if I'd left it out,
Yes.
right? And then somebody would have put it in. Anyways, okay, so I'm going to stop sharing this and I'm going to hand over controls. Guy's going to cue me. So what we're going to do for all of you in the virtual room, I'm going to go off camera, but I'll be controlling the slides here. And I know Guy's probably going to turn off his camera. When we go into the open conversation pieces, will definitely be cameras on for our panel. Okay, so I'm going to switch over here to our next slide. And Guy, you cue me as to how you wish to go.
Okay, well, just as I say, you don't want to see my ugly mug through this whole thing, so I'll be shutting my camera off. And we'll go through the presentations. There's a few locations there where there will be possible pause, asking for perhaps some additional comments from Gord and Eric. And at the end, of course, we'll be open for Q&A. Anyway, Joanne, thank you very much for inviting us to do this thing. And the objectives, I guess, for this session are how continuous insulation will improve thermal efficiency and at the same time reduce concealed condensation potential in walls. We will review, I guess, the regional above-grade insulation requirements and recommend assemblies that might be the most appropriate for those locations. We will do the same for below-grade basement walls and suggest insulation strategies that again meet the thermal requirements and again might address potential moisture issues. We'll show how continuous insulation can enhance weather-resistive barrier and air barrier properties and characteristics of walls, and maybe highlight a few air tightness improvement methods. Next. Thermal performance of walls is enhanced because continuous insulation reduces the thermal bridging effect. As you all know, a frame wall contains a significant amount of framing, and wood is typically 3 times more conductive than cavity insulation. The top wall assembly shown represents a 16-inch on-center 2x6 wall with a cavity insulation of R19. Taking into the effect the higher losses from the framing reduces the R value from 19 to an effective R value of only 14.7. Although we won't be discussing steel studs in this session here, steel studs, because of their high conductivity, are even more drastic in their loss of effective R value. That same wall with an R19 bat would effectively only work at about 8.15. Next. A quick look at 3 16 on center assemblies here show how CI affects the effective R value. On the left is an R22 wall using OSB as sheathing, and that R effective value, considering, let's say, air films only on the interior and exterior, is about 17.1. That same wall, but with the simple addition of an R5 continuous insulation, reaches an R effective of 22. And just for comparison, a 2x4 wall with R14 cavity insulation and an R7.5 continuous insulation gets an effective R value of 19.3, which is actually higher than the R22 wall. Next. The drop in effective R value is greatly affected by how much framing is contributing to the thermal bridging. ASHRAE recommends we use 25% of the wall area as constituting framing. The National Building Code recommends using 23% and 20% for 16-inch and 24-inch on center construction as the framing factors. The real percentage of how much wood is in the wall can actually be higher due to the large window openings in some cases, enhanced structural framing, etc. Next. CI, continuous insulation, I'll refer to CI from now on, works best at reducing thermal bridging by being installed over the entire framed area. It's preferable to install CI on the exterior from a moisture control point of view. And interior CI of the same R value, while it gives you the same equivalent effective R value, will actually increase the potential for wall condensation. We'll address that a little later. Next. We mentioned that infrared thermography here will show a real effect of continuous insulation when installed over framing. The left picture, it shows a wall with conventional sheathing and no continuous insulation. The outline of the framing is clearly evident, and the lighter color at those locations, it simply indicates higher heat loss. The continuously insulated wall on the right shows a much more uniform and lower exterior surface temperature. That basically confirms lower heat loss over the bulk of the entire wall assembly. Next. We mentioned that CI reduces thermal bridging, resulting in potentially better effective R values. But what does it do to the thermal regime across the wall assembly? Here are 4 different walls when exposed to constant 70-degree F interior and a 14-degree F exterior temperatures. What is important to show is that the temperature at the batt exterior sheathing interface, whatever that might be. A conventional wall with R22 and OSB, as shown on the left, has an interface temperature of 18 degrees F under those conditions. If you use an R20 batt and R5 continuous insulation, that temperature rises to 28. Go to the R14 and R7 and R7.5 CI, it jumps to 36. If you want to increase that CI from 7.5 to 10, you increase that interface temperature to 39. Now, I will point out that these are based on static exterior temperatures. In real life, of course, the exterior temperature will fluctuate from fall through the dead cold of winter and back into spring, greatly affecting that interface temperature. This is key in determining which CI insulated walls are best for condensation protection. Next. Gord, Eric, do you have any comments on this section before I move on?
Well, I think the most impactful in today's world, when we think about affordability, we think about smaller houses, we think about the objectives of both building more houses but more efficient houses. I really like that idea of the 2x4. Could we go back to 2x4, notwithstanding structural issues? Pretty interesting, right? To see the change both in terms of the effective R value and the reduced risk of condensation within that wall because you're warming up that first surface. I think it's a real lesson for folks on the call today. I noticed there was a number of designers and architects. Wonder if we could think about going back to thinner wall assemblies with higher levels of insulated sheathing. Pretty instructive as a good start.
Yeah, and at the same time, Gord, it may affect the cost of the walls as well. In that situation, the 2x4 with continuous on the outside, that was the norm in the 70s until people interpreted the R20 requirement as I need to go to 2x6. Good point. Good point.
Right.
I will just quickly add that a frequent question that comes from builders and designers when you go with the thicker CI, especially with the foam board at the exterior, is what about heavy cladding, or how do I install that? So just to know, there's plenty of information already designed by the continuous insulation foam coalition sheetings that could be available. So it is more accepted now, more used, and there's way to go around that and keep the efficient on site. Thanks.
Yeah, thank you, guys. Okay, we mentioned that the thermal bridging results in potential better, but I guess we'll now address some current regional code insulation requirements and how CI can actually be used to find out the best options for above grade walls. Different jurisdictions in Canada, they don't necessarily follow the same method in prescribing wall insulation R values. Some simply call for a minimum R value based on the total nominal R value from the inside air film to the outside air film when calculated from through the insulated wall cavity. This is typical of the Quebec code for wall requirements. The second way is to prescribe the total R value of the BAT and CI combination as used. This is used typically in Ontario with their SB12 requirements. This method and the previous one do not reflect the true effective R value of the assembly because framing and wall components inboard or outboard of the BAT and those outboard of the exterior sheathing are not taken into account. The use of Table 9.36 in the National Building Code helps to determine the effective R value of that particular location's combination that's recommended. Let's go to different jurisdictions now. Next. Let's go to Ontario, and Ontario uses the supplementary bulletin SB12 for prescriptive insulation requirements. This is not saying you can't use modeling tools. Those can be used to determine, an acceptable wall situation. But Ontario is typically divided in two zones, as shown on the bottom left map. And each package associated with the SB12 is associated with ceiling, basement insulation, window door types, HRV efficiencies, hot water heating efficiencies, heating systems type, and others. The top portion shown in this case is the requirements of CI BAT combinations for a 92% efficiency natural gas heating system. You'll note that the compliance packages available require some form of CI ranging from R5 to R10. All of them, except for compliance package A1, which allows walls without any CI. This actually new SB12, it's an improvement over the previous one, which contained approximately 13 compliance packages for gas heating, and very few of them CI requirements. The bottom table, of course, shows the requirements for electric heating. Next. Quebec's above-ground wall insulation requirements are simple, and they use the total nominal R value of the wall assembly components at the cavity. They separate their climate zones in areas of under or over 6,000 C days, heating degree days. Demographically, over 90% of the construction occurs in regions less than 6,000. The assemblies, again, do not reflect the actual effective R value because framing is not taken into account. But to Quebec's credit, a minimum R4 of continuous insulation in the assembly is mandated, but its location is not specified. As mentioned earlier, the exterior is the location of choice. The importance of this will be shown a little later. Next. Manitoba, a cold region, has the lowest above-grade wall insulation requirements, but at least prescribes those requirements using the effective R values, taking into account framing and wall components. The Manitoba climate zones are 7A, 7B, and 8. No continuous insulation is mandated to meet the required effective R values, and in most instances, none is required to meet the relatively low effective R value of 15.9. In fact, no CI is required with their standard building practice. This, in fact, is not really a safe approach, as we'll see later. Next. British Columbia, on the other hand, has stepped up its above-grade wall requirements with their current 2023 STEP code, which includes requirements exceeding those prescribed in the NBC Table 936.2.6 for all BC climate zones. With these enhanced effective R values requirements, it's necessary to use CI to reach levels even as CI is specifically not mandated. Next. For all other remaining regions, the country's NBC 9.36 is used for establishing the required values. For your information, installation requirements for the 5 different locations illustrated so far are those applicable for housing with HRV, operating HRVs. And the placement and quantity and wall insulation of that CI, again, as we say, will definitely control condensation issues. So let's take a look at that now. Let's first set some things straight with respect to condensation. Concealed condensation in the frame wall is predominantly, controlled by exfiltration and leakage of warm air in the insulated cavity, not vapor diffusion. Condensation will form when the dew point of the interior air is reached in the cavity or any location within it. The coldest surface is the interior face of the exterior sheathing, in other words, the batt and sheathing interface. A warmer cavity, of course, will have less potential for condensation than a cold one. And CI promotes, of course, warmer cavities because it's an insulation. And this risk for potential condensation will be greatly dependent on the exterior climate dynamics over the entire heating season. Next. The top figure shows what I am alluding to. The batt wall sheathing interface, whatever it might be, is the coldest location in the wall. Exfiltration leakage of interior air through the batt will cool that air gradually and potentially allow condensation. The probability of this happening is partly dictated by the bottom left figure. There is a total outboard R value of exterior sheathing and total inboard R value from the batts to the interior components. The ratio between this outboard R value and inboard R value basically is a good indicator of the potential or protection level against condensation. In other words, the bottom right table basically says this is the kind of ratio we suggest to reduce potential condensation in your wall. Effectively, what they're saying there is we're suggesting how thick your insulation coat needs to be to reduce your condensation levels in the wall. Next. Good place to start is the Ontario Compliance Package A1, which is the R22 batt and no CI, typically OSB. Let me explain that graph. This is a dynamic trace of the batt OSB interface temperature from fall to winter and back into spring. This interface temperature is represented by the curved line, starting high in the fall, down to the bottom in the winter, and up again in the spring. The horizontal red line is the dew point temperature of what we have chosen here for demonstration purposes of 73F and 35% relative humidity indoor air. That dew point happens to be 6 degrees C, as shown on the graph. The outside air temperature variation drives the interface temperature down to its lowest point in mid-January to about -5. The time during which the interface temperature remains below the dew point signifies likely condensation periods at the interface should we get outward leakage of air. In this particular wall assembly in Toronto, the so-called I'll call it residence time of the dew point in the wall is about 5.5 months. Also, the A1 package of R22 CI only delivers about 17.3 effective R value. The RORI ratio that we alluded to in the previous slide is a dismal 0.5, not a very warm winter coat. Next. Toronto again, and the same exterior tent conditions. Let's look at the behavior of a compliant package A3. And as mentioned by Gord earlier, perhaps a much better situation using a 2x4 with an R14 bat and a continuous installation at R7.5. As expected, this is a much warmer coat, and it's reflected by the warming of the bat CI interface. The dew point residence time in this case has been reduced to 2.5 months, and an effective R of 20.8 is reached. The high RORI ratio, 0.57, makes this package acceptable to degree day areas of around 10,000 degrees C days, which is basically any region in Northern Ontario and most Western Canada climates. Next. In some instances, 2x4 framing may not be acceptable from a structural standpoint. In that case, one can opt for SB12 compliance package A5, which recommends R19 BAT and an R10 CI. In this instance, the RO and RI ratio has not changed much because we've increased both the CI and the BAT R values. This A5 package results in dew point residence time very similar to the 2x4 wall mentioned earlier, to about 2.5 months. The wall, however, has a very good high cavity R value of 31.3 and a high effective R value of 27.1. Next. Okay, that last wall that we saw, why don't we move it to Sudbury, which is a much colder climate than Toronto. The colder fall to spring temperature dynamics, of course, will then result in dew point residence time of about 4.5 months. In other words, that coat is not thick enough to get the same performance as the 2x4 wall or the R19, R10 in Toronto. The latter, fortunately, is not permitted in Ontario because Zone 2 does not permit, let's say, the R14 and R5 CI application. Next. Let's change provinces and look at Montreal. We're using the same indoor conditions. Fortunately, R4 CI is mandated, but location not specified. The graph here represents the bat shielding interface when the R4 CI is on the interior face of the framing, which is not the location of choice. Excuse me. I mentioned that the interior placement is not desirable, and this is why. The interface temperature is below the dew point for about 6 months of the year. That's not a good situation. The nominal cavity R value at 28.6 meets their code, but the effective R value does not take into account any framing, and that would be about 24.2. Next. This is what happens when we move the R4 to the correct location on the outside. The dew point residence time is reduced to 4.5 months, and the nominal and effective R values essentially remain unchanged. And it easily meets their required 24.5 nominal R value by their code. Next. A much better solution with 2x4 framing would be, if it's acceptable, is to use R14 7.5. Residence time is again further reduced down to 3.5 months, and the Quebec installation requirement of 24.5 is met. Oddly enough, this is the type of wall assembly that was marketed by Dow Chemical in the 70s to exceed their current 70s energy code requirements and reduce condensation potential at the same time. Next. Now let's go to a much lower, colder area, Winnipeg. And their current wall insulation requirements is R effective 15.9, which is pretty low. This is met by simply using an R19 cavity insulation with no CI. And with that low RORI ratio of 0.06 from the absence of the exterior, this wall remains at a risk of condensation for 6.5 months of the year. I can't understand why walls would be built that way, especially in that climate. Next. Much better solution, provided the 2x4 is accepted structurally, is to use that R14, R7.5 CI combination. It would reduce the condensation potential to 4.5 months, and again increase the R value from 16 to 19.2. Not shown in this slide is if we had elected to use an R19, R10 combination scenario for a further improvement to an effective R value 26.7. The potential condensation risk for using an R19 BAT R10 continuous insulation would be, about the same as far as the residence time, but the effective R value would be significantly higher. Next. Despite being located in a relatively mild area, Vancouver's required effective thermal resistance is 21. In fact, this is the requirement for BC climate zones 5, 6, and 7A. Only 7B has a higher requirement with an effective R value of 22.5. To meet those effective R values, CI is almost necessary unless cavities greater than 6 inches depth are used. Here is what we show that the mere use of a small 2.5 R value CI over an R24 BAT insulated cavity just meets the required effective R at 21.3. Despite the low CI and RORI, condensation time is limited to only 2.2 months. This is due, of course, to the effectively mild climate basically of the Vancouver area. Next. If we use the R19, R5 CI combination under those particular interior conditions, there is no risk of exfiltration-induced condensation at any time. The BAT interface temperature never gets cold enough for this condensation to occur. Again, the effective R value of 21 is slightly exceeded with 21.7. Next. After examining the different BAT and CI scenarios that we've shown across the country, there's a list here of show 4 wall assemblies for CI sheath walls, and these recommendations meet both the RO requirements prescribed by the NBC and provide the specific wall insulation requirements mandated by each specific regional code. First wall, the R14 with 7.5 CI. That would be very suitable for Ontario Zone 1, Quebec less than 6,000 degree days, most of the maritime provinces, and would be suggested as a better alternative to the R22, R19 no CI BAT condition in Manitoba. The R value would be very good. The RORI is high, 0.63, meaning it's a very protective wall against condensation. The next wall assembly, R19 plus 5. That's also as an alternate for Ontario Zone 1, Quebec again too for less than 6,000, and the maritime provinces and Manitoba as well, specifically when structural capacity is needed instead of the 2x4s. Next. R14 plus 10. This is a very good wall. Ontario Zone 1, Quebec over 6,000 degrees C days, maritime provinces, Manitoba, essentially any cold climate. This would be acceptable. If structural capacity is needed, you want to keep the R10 CI out on the outside and use an R19. Again, the RORI is high, still at about 0.52, which provides basically excellent protection. That last wall on the right is basically suitable for any zone, any region in Canada. It'll provide you the effective R values needed and also gives you adequate condensation protection. Next. Any comments from Eric? Comments?
And maybe I would just take the opportunity to remind that CI has been adopted for commercial walls since long time, what they tend to call the perfect wall, what the continuous insulation is positioned very often 100% of the exterior of the wall in a commercial building. Probably not a good idea to do the exact same thing on residential, but it's just to demonstrate how effective CI can be, already been adopted in a commercial building and sometime as well in this application. If you can have a narrower wall, like a 2x4, it may, especially if you're a rental, give you some extra space at the interior of the building as well. So thanks.
Yeah, an additional point, and this refers to steel studs. You have no choice with steel studs and installing some sort of CI. And in some cases, it's more economically viable to use entirely CI to provide your insulation requirement on steel stud construction.
I think that's the instructive part, right? Key is that because steel stud walls had such a low effective R value, they had to go to CI sooner, but therefore the residential industry gets to learn from that. And when we talk about, well, how do I attach cladding? Go look at the commercial folks. Well, how do I do
Exactly.
how do I do windows? Let's look at the commercial industry. So it shows for those who say, I've never done this before, we'll walk across the street to the strip mall being built, and you'll see how you can impact that continuous insulation. But I do think it's worth just highlighting again that every time you add continuous insulation, you reduce I love what you said, the resident time, that the dwell time of moisture. There's our moisture risks in walls. You can minimize the moisture risk by making walls more airtight, not allowing air leakage, or you can minimize, and I'll say or you can minimize by adding continuous insulation. Every time you add continuous insulation to the outside, you've reduced your risks of condensation within walls and improve your thermal performance. And now we're learning, if you do it right, you can reduce the thickness of the wall by going back to 2x4 and using more continuous insulation. Pretty interesting.
Yep. All good points.
There was a question that came in too
about
what is considered an acceptable number of months for there to be dew point residence time in a wall.
Good question. I mean, that bad wall that I said in Winnipeg that's got, a high RO or a low RORI is the worst wall. That's not necessarily saying that the wall will rot. This basically says the conditions are much longer for condensation to happen. And, those curves were if you did get significant amount of exfiltration through the wall. That the good wall there, the 2x4 with R7.5, okay, it had lower reduced time. There is no magic number, unfortunately, Joanne, for your person who asked the question. Obviously, you can just say that the lower the better. And typically that 2x4 wall with R7.5, I mean, hundreds of thousands of homes were built like that in Quebec in the 70s and early 80s. And none of them, they're still standing up. Let's put it that way.
Yep.
And I'll add my 2 cents on this. When Winnipeg went to R19 back in the 80s, they did have moisture problems. They resolved it by making walls more airtight. So even a large production builder in Winnipeg routinely are under 1.5 air changes, and they needed to be there in order to resolve or minimize the chance of moisture risk. So that's how they, over time, have resolved it. And I like these thoughts, the lower the better. The other thing we need to understand is relative humidities are going up in houses. People's understanding of what is comfortable. I used to live out west, and routinely we kept houses at 15 to 20% relative humidity. There's less chance of condensation in the wall. Now homeowners would say, well, geez, that's not healthy. I want to be at 35 or 40%. So your risks have gone up. So over time, you want to reduce your risks to allow your homeowners to have higher levels of relative humidity. 2 ways to do that: make your wall assemblies tighter, and add insulated sheathing the outside. Risks on the way up, we need to find a way to mitigate that risk.
Yeah. There were a
Yeah,
couple of
no
other
problem.
follow-ups that came in, Guy, but I'll hold those for you till we get through
Yeah,
the next
okay.
section if you like. Not a problem.
Yeah, let's go to the next section, please.
Oh, great. Okay.
Yep. There's also benefit for using CI in some form for the insulation of basement walls too. However, these walls are not subject to the same thermal stresses that a wood frame is subjected to, especially over the varying height of or depth where it's located. Structural concrete does not behave the same manner as wood frame structure, but the exterior RORI basically concept does apply to some extent. This basement wall insulation will require different strategies to basically to meet two things. Meet the requirements of R value for the zone or the jurisdictions, and limit some potential moisture issues. Next. In normal residence, Enercan used to state that about 24% of the heat loss uh, originated from the basement walls. Of course, with the increased insulation and air tightness of more modern construction, that percent will definitely vary. The heat loss from a basement wall, and of course, is not equal over its entire depth. A study by the University of Kansas showed that for a full height uninsulated 8-foot basement with 1 foot exposed, that over half the heat loss occurred at the top exposed 1 foot location. Soil has some valuable benefits of buffering heat loss and provides some insulation as we progressively go deep down the wall. Let's look now at some of these local code insulation requirements. For Ontario, their SB12 compliance package applies again, but it calls for a total nominal R value based on bat and continuous insulation. The presence of framing slightly reduces that nominal R value totally by about 10%. You will note that some CI is required in all climate zones, and the placement of the CI, unfortunately, is not mandated in these compliance packages. Next. The Quebec region does not mandate the use of any CI for insulating basement walls. It only requires a minimum nominal R value calculated through the insulated portion of the assembly. If the assembly is bad insulated, framing factor will affect the effective R value, and that will be significantly reduced. Manitoba, for its above grade wall requirements, requires a relatively low R value for basements. Note that these values are just like, as I said, the above grade walls and are reflectively, only 15.9 over the 3 zones for Manitoba. Framing factors for basement wall insulations are much lower than above grade. So this basically affects, it goes in your favor when trying to calculate the effective R value. The framing factors of 16% and 13% are used for or suggested for 16-inch and 24-inch on center framing when calculating the effective R value for basement applications. Next. British Columbia uses their 2023 step code to mandate minimum effective R values for basement walls. And basically, it's an enhanced 9.36 table from the National Building Code. And it requires effective R values ranging from 19.6 to 22.5, but again, does not mandate the use of any CI to meet those requirements. All insulated frame, all CI, or combinations thereof can be used. Reduced framing factors are again to be used for framing portion of to calculate the actual assembly effective R value. Next. There are many options to insulating basement walls. You can have the plastic film faced fiberglass blanket. This method, while expedient and low cost to install, may provide anywhere from an R12 to R20 continuous insulation. and is required typically in Ontario, but has some serious drawbacks. This insulation cannot be properly used if the homeowner is wishing to finish the basement. There are other moisture problems. You can have moisture entrapment within the blanket that leads to mold issues. This is especially the case with new construction. Combinations of continuous insulation and insulated frame assembly on the interior can be used, as shown in the middle two scenarios. And finally, there is what I'll call a hybrid insulation scenario with the with a water-resistant CI on the exterior combined with an insulated frame assembly on the interior or a CI frame assembly on the interior as other options. Let's look at these different strategies here. For all the scenarios we'll show, we will set the interior temperature to 70 Fahrenheit at 45% humidity and the outside temperature at 30 degrees. Now the associated dew point with 70%, 70 degrees, 45% RH is about 48 degrees Fahrenheit. This situation is probably only representative of the exposed portion of the basement wall. The outside temperature of the outside face of the concrete as we go deeper and the interior face concrete on the concrete will also be higher, typically as high as 45 degrees Fahrenheit. This scenario is an R20 BET, either as a blanket or an R20 framed assembly with an interior vapor retarder. Moisture trapping is common in this scenario, especially in brand new construction with fresh concrete. Mold issues and potential deterioration of the framing is also possible. Exfiltration of interior air through the bad insulation is possible, and like in frame assemblies, condensation may occur at the coldest interface. That coldest interface is, of course, the bad concrete one. With those interior-exterior conditions, the top portion of the wall may be 32 degrees Fahrenheit and certainly sufficient to promote condensation, and in fact, in a lot of cases, frost. Next. Various combinations of interior installed CI and an ensuing insulated frame assembly can also be used. We use the same interior and exterior conditions. The table shows the interface temperatures between the BAT and the CI interface with interface A, and the coldest interface between the CI and the concrete wall. The combinations are 5 CI and R12 BAT, a 10 CI on the wall with an R12 BAT framing on the interior, or an R10 CI and an R19 BAT construction interior face of the CI. There is potential for condensation on both interfaces of the three options of CI BAT, with only the R10, R12 appearing to be marginally safe under those conditions. From a thermal resistance point of view, of the bottom two combinations would meet the Canadian region effective R values, so only those two would meet them. Next. This strategy involves locating CI on the exterior of the basement wall and an insulated frame cavity on the interior. We're starting to look like something similar like an above grade wall, except we don't have framing, we have concrete. The various exterior CI and BAT interiors are in the combinations that we've examined is an R75 CI on the exterior with R12 interior, R10 exterior, and an R12 BAT, R15 with an R12 BAT, and then all R20 on the exterior with no BAT on the inside. In other words, complete exterior basement wall insulation. Because of the insulating coat provided by the exterior CI, that interface will significantly get higher as we increase that, I'll call it again, the ROII ratio. In fact, as expected, the values are high and in most cases above the dew point temperature of the interior air. In other words, that cold interface A will not support condensation in the last two scenarios at the bottom. Next. Instead of using glass batt interior insulation in the previous combo, we can replace that with CI. The combinations here are exterior of 5 and interior of 15, exterior of 10 and 10 on the exterior, or 15 on the exterior and 5 on the interior. The ensuing temperatures at the cold interface on the interior face of the concrete, interface A, progressively get higher from 40 right up to 58. So very unlikely chances of getting condensation in the last two scenarios. Next. When the interior CI is either fibrous or rigid foam insulation, it's installed in direct contact with the cooler surface. And what's important is that the interior air convection be reduced or completely eliminated. Any moist air reaching that interface, as we've shown in the past slides, will condense based on the last different scenarios and the interior temperatures and humidity. In some cases, frost can form as well. For CI on the wall, a continuous bead of compatible sealant at the top portion between the XPS CI and the concrete is suggested. Sealing the CI panel front joints is also recommended. Next. This picture shows XPS CI installed on the interior face of a concrete with its front joints taped. We anticipate that, as recommended, a bead of sealant would have been installed at the top between the foam and the concrete wall. This framing will, of course, reduce the effective value of the assembly, but not significantly, because we've got basically anywhere you could be using 24-inch on centers, and the framing factor could be quite low. Next. As pointed out earlier, the use of complete CI on the exterior of the basement wall is the ultimate solution. There is no insulation reduction from any wall framing factors. Indoor space loss is nil. There is no risk of interior concrete surface condensation. The insulation in those cases installed vertically, with fastening only at the top portion. There unfortunately are some issues when installing a thick R20 insulation on the exterior. Let's look at those. Exposed exterior insulation must be protected from physical and UV damage for at least the upper portion. When thick CI in the range of R15 to R20 is installed with brick veneer claddings, the standard and standard thickness wall sheathings, a potentially unacceptable aesthetic situation may occur with the outer face of the basement wall and veneer not being in the same vertical plane. There is also a significant thermal bridge at the top of the basement wall. Next. A solution to the aesthetics and thermal bridge is to install exterior CI only below finished grade and install the same R value CI on the interior with an overlap of at least 4 times the concrete wall thickness. The termination of this insulation at the wood plate will reduce the thermal bridging as well. The alternative, of course, is to use rigid CI entirely on the interior face, but again, in this case, you will have to make sure you do not have any condensation or convection behind the board. Next. Excuse me. Thermal bridging is not an issue if the above-grade CI insulated wall is in the same plane as the below-grade surface. This is especially the case in above-grade CI where the CI is 1.5 inches or thicker, and the above-grade wall cladding basically is furred out and is often recommended by most cladding manufacturers. Below-grade CI in contact with soil and it must have some moisture-resistant characteristics. Next. There is a potential issue when you are using thick continuous insulation for the above-grade walls in combination with brick veneer claddings. In most cases, a thicker, more expensive concrete basement wall would be needed. This can be addressed by fastening a steel shelf angle at the top of the basement wall for brick support. This is best when used with XPS interior and XPS interior-exterior hybrid wall strategies. The best is when used with XPS interior. The thermal bridging in this case is eliminated because we do terminate at the plates. The thermal bridging is basically, eliminated because we have continuous insulation provided by both the above grade cladding insulation and the interior face. Next. A second option to address thick above grade CI with brick veneer is specially forming the top of the foundation wall to provide an outward extension of the concrete. This could effectively allow the more desirable R15 interior exterior CI and R5 interior CI for providing the required insulation value and condensation protection. Next. Whenever rigid foam insulation is used on the exterior, it will be in contact with soil moisture for the life of the installation. Any absorbed moisture will result in a reduced R value of that product. ASC standard 3201 addresses this by suggesting effective thermal resistances for various EPS and XPS insulations for applications of this type. The standard Canadian CAN ULCS 701 value for XPS is accepted at R5 per inch. But in vertical exterior basement wall insulations, it should be considered at R4.5 or used as 4.5 per inch as per this standard. For R4 and R4.3 standard EPS products in the same application, ASCE recommends using R3.2 and 3.4 for those two products respectively for the purpose of long-term design. Next. Any few more comments from you guys?
I would say that just to reiterate that the use of CI in a foundation, when you do that 100% of the exterior, and you are able to manage the thermal bridge. Let's say there's no brick, as one of the example has been shown, allows you a lot of time to leave the concrete wall exposed in the basement, and so reduce the cost of finish that, and also may help for future code that will require in some area provision for floating and stuff like that. So there's several advantages. And also, if you get the concrete exposed in the interior of the basement, it also helps to with the mass effect. Eventually, it could be a reservoir of energy to kind of minimize the peak of energy consumption for heating, stuff like that. So there's a lot of benefit down the road. So you may just think about that the way you build your wall right now, and see if there's opportunity for you to use less thick brick and maybe go with veneer, stuff like that, which can be installed like a cladding. Also save some money, help you out to put the insulation at the outside of the foundation, and gives you also eventually that will be a positive effect when the code will count for a embodied carbon on the material, knowing that concrete and masonry is high in embodied carbon. So few thought I wanted to share. Thanks.
And then I'll add again the understanding that we said, if you want to know how to do continuous insulation above grade, go look at the commercial industry because they're already doing it. In terms of basement insulation, there was research done both in United States, Minnesota specifically, and in Ontario back in the 1990s on how do we solve basement moisture issues. In Minnesota, it's now a state code that you cannot insulate on the inside in new construction. You must insulate. You must start your insulation on the outside. And as a result of that, they have all kinds of really, I'll say, creative ideas as to how to finish that above grade portion, because that becomes the big knock, right? How do I finish that above grade? And they have various pieces. You mentioned cement board. They've got an embossed metal. They've got a rollout plastic product, parge coatings. So we take lessons from other climate zones, other places to say, I wonder if we could be more cost effective, have higher performance. And in this case, insulating to the outside of a basement wall, some really nice synergies when you match up the exterior above grade continuous insulation to the exterior insulation on the basement wall, as long as I can find a way to finish it. So don't despair and look for new ideas to how do I can make these changes.
Yeah, appreciate that,
Awesome.
Eric. Yep.
Thanks. And we're just in that home stretch,
Yeah,
Kate.
I
We'll
can
definitely
quickly
have
go
time
through. Yeah.
for some questions too, because there were a couple. So I'll move over to your next slide then.
Okay, I'll go through quickly for the rest. Yeah,
Yeah.
thanks. You know, insulation levels are increasing. We're putting better windows and doors. So the unintentional leakage, I guess, would be slightly reduced. This is an US DOE approximation of sources of air leakage. Of course, will change depending on any particular situation based on the house, the size, the volume, the air tightness, construction character, the characteristics of the windows and doors. What's necessary though is that windows and doors be properly installed, and we recommend, of course, the CSA A440 standard for that. Next. To put the importance of air leakage in context, this is the heating dollars that would be required to compensate for air leakage. For a Toronto two-story, 3,000 square foot house equipped with 92% efficiency furnace and a gas cost at 15 cents per cubic meter, the OBC recommends a maximum or suggests a maximum air leakage of 3 air changes per hour, which is super high. Their standard maximum would be 1.5, 2.5, and their so-called high performance leakage rate would be a maximum of 1.5. In this case, this would represent $1,600, $1,300, or $800 per year associated with that leakage. So air leakage control is not increasingly, has always been important. And I think Gord is very good at that. I mean, he knows all about that stuff. If we move that Toronto house to Edmonton, those dollars, and based on the same size and cost for gas, would be up by 44%. Next. DuPont Styrofoam CI, when it's properly installed, provides an effective weather-resistant barrier, and it's also been tested the ULC 742 and has achieved a Class A air barrier rating. This rating applies if the product is installed over or with or without underlying OSB, can be used with 2x4 or 2x6 framing. And as was discussed earlier, it's not absolutely necessary to use continuous insulation to meet the requirement levels in Canadian jurisdictions, as shown on the right, where I am showing here the inferior wall construction with no CI. In those cases, home wraps, Tyvek, commercial wraps can be used and with the lap seal penetrations and perforations properly sealed, you can get an effective air and water resistant barrier. Next. A belts and suspenders approach can sometimes use with Tyvek installed either behind or over the CI. If installed behind, a reduced nailing pattern can be used for the CI since the rigid CI styrofoam will be fastened through it to the framing. Installing the Tyvek over CI that's greater than 1.5 inches requires much longer Tyvek fasteners. Next. Sealing of rim joist spaces around plumbing and electrical penetrations and exterior walls also reduces the unwanted leakage and potential moisture ingress issues. Next. As part of 440 standard, proper installation of windows and doors require proper sealing around the openings. And in those cases, most cases, low expansion, 1-part polyurethane foam seal is basically the effective way to do it. Next.
Okay.
I think that's it.
That kind of brings us to just really some a wrap-up question, but also asking some questions out loud as well and kind of getting thoughts from everybody too. So I'm going to launch this poll, Guy, because I think that's going to help everybody too. So as we open this up, and I'm going to launch the questions too, this is a poll for everybody to kind of answer. Like, we want to understand how, after listening to Guy share his thoughts and with the engagement of Eric and Gord too, and their experiences, how likely are you to apply some of these insights and strategies into your new projects? So we'd like to open that up there and keep that open for a few moments. But after your second section, Guy, there were a couple of follow-up questions. That first initial question around the acceptable number of months for there to be the dew point residence time. There were a couple of follow-ups in the Q&A. So Richard had asked, am I correct that in R20, R7.5 give you a ratio of 0.375, and is that considered too low? Or is there a ratio number that you consider to be too low?
Well, I guess I can always throw them into the what the National Building Code calls for, the suggested ratios for that specific heating degree day he's located in. As
Okay.
long as you meet that, that's great. And if you're even higher, if that ratio is even higher, that's even more protective.
Okay.
So what I'm saying, hell, if he wants to have, let's say, the total R value through his cavity, let's say R20 and R7.5, if he wants to keep that same total R, but use less on the inside, more on the outside to give that same value, his RORI is going to be rising and his protection is going to be better. So I'd first consult with the NBC, I guess, table,
Mm-hmm.
and he should be at that level. He's in pretty good shape for Northern Ontario, as far as I'm concerned.
Yeah,
And
perfect.
again, as Gord mentioned earlier, that's fine. Yeah,
Mm-hmm.
the insulation is keeping things warmer than, let's
Mm-hmm.
say, conventional sheathing, but at the same time, you still got to control any potential air leakage to the outside.
Right.
Those two things are critical
Mhm.
together.
And that's a good example in the chat. Jim was asking about what if you did a double 2x4 wall with cellulose? Well, now you have extreme amounts of insulation in the cavity. The backside of the cavity is going to be
Yeah.
colder, so you need that wall to be even more airtight. The more insulation you put in the cavity, the more airtight you want it to be, not for energy efficiency, although it is, but to resolve or limit the amount of warm, moist air that could be condensing inside. So that's why continuous insulation is a really nice win-win. It can be your water barrier, it can be your air barrier, and it improves your thermal control and it reduces the risk of condensation inside that wall cavity. You can't get rid of the risk altogether, but you can dramatically reduce your risk by increasing the ratio of the insulation on the outside versus the cavity.
And that's basically the origin of that table in the National Building Code. I mean, they did admit that yes, we will get condensation in the walls, but we want to limit it. And the way to limit it is keep it warmer. And this is what we suggest for different cold climates. So and you choose your wall assembly to meet that. And that's it.
Yeah,
And
perfect.
just
Eric?
remind that the new housing with the new performance, it's more like a system, like a little industry itself. So it's different approach than the whole wall, and we're counting on Mother Nature just to do the air change. So it's very
Yeah.
different way to approach that.
And in my summary remark, I would say this, knowing what you've seen, what folks have seen, hopefully they all understand that if we're not doing continuous insulation now, you will be. And if you're worried about getting continuous insulation, say, how do I do that? Well, from a basement perspective, find out what's happening in Minnesota. And guess who helped with that? DuPont, Dow at the time, and now DuPont, finding the right methods. And then if we think about above grade, how do we do that? Well, look at the commercial world and who helped with that? Eric and Guy, right? You helped implement continuous insulation on exterior walls in commercial buildings. Lots of expertise within the family of companies that says, hey, we can help you get continuous insulation to the outside of your buildings. It's not, designers have to understand the differences, contractors, installers. It's absolutely possible. Lots of folks doing it. Learn how to do it as quickly as possible because it reduces your risks and increases opportunities for better performance.
We should go back to the future with
That's
with
right.
continuous installation, go to the 70s. I mean, that was the norm. And because okay, it met code, actually it exceeded code. And at the same time, I mean, they were so protective from any condensation issues. Yeah.
Perfect.
And
Any other closing thoughts, Eric or Guy,
no,
as we
just
wrap up?
No,
just
this
just
time.
just I just want to mention that the 2x4 wall, it's something that tried to promote for at least 18 years and it got a lot of pushback. I understand there's some reason that makes sense, but it's a thing that we should keep in mind and see if we can reduce the usage of wood in the building and help us out, technically speaking, as well as save money and stuff like that. So I don't know. There's probably a way that the wood can be reduced and the cost keep it down. The whole goal is to make better performing housing and still managing the cost of building, right? That's the whole thing.
No, that's true. So on that note, I want to thank our panel. Guy, thank you so much on behalf
Welcome.
of the Inner Quality team today. Thank you very much for sharing this information and for sharing a lot more knowledge, hopefully around the CI piece that DuPont provides. Eric, thank you as well for your insights. And Gord, as always, it's a pleasure to have you on any panel. And hopefully everybody has been able to take something away. That's, I guess, the goal at the end of our Ask the Expert sessions with everyone. Our goal here at Inner Quality is for everyone to walk away with some nugget of information that you're going to be able to apply in your everyday practices. So as I said, as a wrap up, thank you very much to DuPont for providing this information and for hosting this session. On behalf of our team, we thank you, our audience, very much for participating, for your questions, for your engagement, and for staying with us. We always appreciate your feedback. So I have a little QR code up here on the screen where you can answer a couple of questions. As we wrap things up, we will send out an email today. You'll all see those in your inboxes. It will have a link so that you can complete this survey too. It just takes a few minutes. It really does help us here at Inner Quality to understand what you take away from these sessions, also what you would like to see. And it also helps our facilitators because we do share the anonymous information with DuPont so that they can also understand what you're taking away from it as well. And it will have a link to the presentation and, of course, to Guy and Eric's contact details so that you can reach out to both of them with any other questions that you might have. But apart from that, thank you everyone for joining us this morning. I was about to say this afternoon. And we look forward to hosting you again very soon. So thank you so much, everyone. Have a great afternoon.
Our pleasure.
Thanks. Bye.
Thank you. Take care, everyone.